Welcome back, everyone, and welcome to everyone on the live stream. We're very excited now to get to hear from the final prize winners. There'll be 3 presentations, and then we'll have, again, a panel discussion where there'll be time for Q&A. The first presentation will be from Kristin Porter. She's a senior research associate at MDRC, and she heard about the challenge through Twitter and decided to get excited with some of her colleagues, and they ended up producing some amazing work. So let's hear about that now. Thank you, Kristin.
Great, thank you. Yeah, I just want to point out that my colleague Tejame Gadgil, who did some heroic last-minute programming, is here today, and as well as Denny Chen, who didn't get to join us on the Fragile Families Challenge, but she works with us on other predictive analytics projects at MDRC. So first, a little bit about MDRC. We are a nonprofit, nonpartisan social policy and education research organization. We design promising new interventions, typically aimed at people in poverty. We also evaluate existing programs with the highest research standards. And we provide technical assistance to build better programs and to deliver effective interventions at scale. So I'm going to start off today by summarizing just some of the key analytic considerations we applied to the Fragile Families Challenge. I'm going to move through these pretty quickly. One, because many other presenters today have touched on these same themes. And also we posted a blog just Tuesday that go into all of these topics. So these guided our analysis in the Fragile Families Challenge. First, we invested very deeply in measure creation, as many, many people have commented on. This is probably 90% of the work in any predictive analytics project that we do. And our goal here is to combine substantive knowledge about the populations and about the data context, as well as automated approaches. At MDRC, our ultimate goal is actually, in many cases, to deploy a predictive analytics system that will be iterated and updated as new data and new information are coming in. So we're trying to figure out a system where we can really maximize automation as much as possible. And while this was very challenging in the Fragile Families Challenge, as many people have noted, it's even more challenging in a lot of the other settings in which we work. We didn't have as great of documentation as we had for Fragile Families. We're often working with management information systems and other administrative data in which the measures are collected in all different time points. They change over time. There's multiple people inputting them in different ways, and they're really messy, which makes the automation even harder. Sorry. The second theme here has come up a lot is missingness. And I'll just point out that we did absolutely no imputation at all in our submission. I've been interesting to hear about some of the different approaches that people took, and I think there's a lot of really good ideas out there. There's a lot of information that lives elsewhere in the survey data that can be harnessed. But again, we were trying to maximize automation, and we also really felt that the missingness is informative. So we went with that assumption, and we tried to harness that information from the missingness by creating measures that included that missingness. There's also been a lot of talk today about feature selection or measure selection. So we focused a lot on that. We typically do, but we also thought a lot about feature elimination. So there's just a lot of measures in the data, either because of the way we created them or just in the ways they were in the raw data, where they just don't provide a lot of information. They're either duplicate information with other measures, or there's mostly missingness, or there's just not enough variation to really provide. So we had some automated ways that we searched through the data and threw lots of things out. And this eliminated a ton of measures. Next, the way we approached it for the model building. At MDRC, when we think about machine learning, we start with defining a learner. And we define a learner as a set of 3 things. One is a set of candidate predictors. The second is a model building method or machine learning algorithm. And the third is tuning parameters that might apply to a particular machine learning algorithm. So for example, it might be a penalization for a regression approach, or it might be the number of trees in something like random forests. So we also kind of come at this where we have no idea for any given data set which machine learning algorithm is going to work best, which tuning parameters are going to work best, or even which set of variables is going to work best. I will say for the Fragile Families Challenge, we only defined one set of predictors, and that was our final big set. But we'll sometimes have a smaller, more parsimonious set that allows us to look at whether simpler models with fewer measures can do just as well. But in any case, we don't know which learner is going to work best in any situation, so we just throw a whole bunch out there. And then we do something what we refer to and is referred into the literature as ensemble learning. So we're looking across a large number of learners, and we can either pick the best one, or we can combine all the information across different learners so that even weak learners and strong learners are coming together, as was described earlier today. Next, I wanted to talk about some of the analytic considerations that we also think about in other settings. So in the Fragile Families Challenge, we were really just dealing with one cohort of data. We were using, we took a cohort and we used part of that for training our model and the rest of it for predicting. But in a lot of the predictive analytics problems that we're working with at MDRC, we're using individuals from the past for whose outcomes are known to make predictions about future cohorts of individuals whose outcomes are not yet realized, not yet known. And this brings up a whole other set of things to think about as we're doing our predictive analytics. So first of all, you have to really think hard about defining your training set and then your prediction, or what will ultimately be your validation set. And so you really want to think hard so that those that are included in your training set look as much like those that are in your prediction set, both in terms of who they are and in the context. And you want to go through the same thought process for the predictors as well. Are the predictors that you're going to have available for those for whom you're making predictions, did they exist earlier and were they defined the same way? Was there more missingness so that people weren't maybe filling it in the same way? There's lots of checks that we do to try to make sure that the measures are not only there, but they're used and have this consistent predictive value. Another thing to be really careful of here, and it's something that may sound really obvious, but that we see people making this mistake over and over again, is they accidentally take information from the future and they put it in their predictive model. So if we're going to make predictions, we have to decide very carefully, when are we going to make those predictions? And then when we're looking back for our training set, for whom we have all kinds of data, make sure that we're only using measures that would be available at the time that those predictions are being made. So for it's like intake to a program, we're not only just using intake measures, but we're making sure that every measure on that intake file was actually entered at intake and not put back in later. Those little tiny mistakes can have huge implications where you think you have this highly successful model and you don't actually. The third thing we think a lot about then is what's the right measure for evaluating the performance of our models. And this, we think a lot, should be aligned to how those predictions are going to be used. So at MDRC, we might be working with programs who are going to intervene on those who have higher predicted probabilities or higher scores for a particular outcome. And they may be trying to save resources. So they might really care about minimizing false positives, for example. In other cases, you really want to be as good as possible as finding all of those that are at risk of an outcome. So sensitivity and specificity might be interesting measures to maximize or optimize against. And this is just kind of something you have to think about in a case-by-case basis. All right, so we were asked to comment on the value of predictive analytics in social science research. So I thought I'd describe really quickly a little bit about what we're doing at MDRC. At MDRC, we are primarily using predictive analytics to improve and target social services. So we work in many policy areas at MDRC, and here's just some example questions from actual projects at MDRC that we're tackling with predictive analytics. So in education, we're asking which students are least or most likely to fail at a high-stakes exam. In employment, we're asking which individuals are most likely to drop out of the training program, or maybe less likely to not reach a particular program milestone. And in criminal justice, we have a project where we're looking at the probability that a defendant will fail to appear for a trial or commit another crime in the interim. So in all these cases, what we're trying to do is use predictive analytics to estimate a risk of an adverse outcome. And this risk is in the form of a score between 0 and 1. So how might these predictions be of help to the organizations with whom we are working? We work in close collaboration with a variety of school districts and nonprofit organizations to really make sure they're asking the right questions that will help improve their programs. And then we provide them with these predictions, that they're using them in a way that will actually be helpful. So they can use these, for example, to target individuals based on their risk level, especially interventions that might be very resource intensive. So doing this, could also increase the success of an intervention if there's a theory that those most at risk or least at risk or somewhere in between are going to be those that have the biggest impact. This could save limited resources, and it can also reduce burden on participants who might not have to receive an intervention that they may not need. This also allows us to look at distributions of risk across sites in a program or across other groups, as well as within those sites. And this can also help us understand who is most or least at risk or somewhere in the middle. So one thing we can do is identify a subset of individuals based on their risk level and just ask the question, who are these folks? We can look at their characteristics by doing like a post hoc analysis of our predictive results. And this can help understand what's driving the risk. Of course, it's very observational, but it provides some clue of how this risk might be mitigated and how we might intervene. So I just wanted to conclude with some thoughts, not a comprehensive list at all, but more on the potential, as well as some of the limitations of prediction in social sciences. I think at MDRC, we're really trying to capitalize on the fact that a lot of the programs with which we work are collecting more and more data. They're getting more nuanced and more fine-grained data, and there's a lot more of that to harness. They're also doing a lot more data integration, pulling in data from other sources. So for example, a lot of school districts, or at least some school districts, are pulling in child welfare data or pulling in data from the criminal justice system, which may help increase the accuracy of predictions of who might be at risk of dropping out of high school. We're also trying to harness machine learning methods, as I described, and our goal is not only to have more accurate predictions, but to really be able to develop a system where we can update and iterate our predictive modeling and extend it to a wide variety of outcomes, and predicting those outcomes at different time points as well. We have this system we can just keep implementing. We're also using predictive analytics to really collaborate closely, as I mentioned, with nonprofit organizations and with data scientists, social scientists, and subject matter experts. And we really think that by bringing all of these groups together and working in close collaboration so that we really, really understand the data, especially in cases where we don't have the documentation that's as rich as we do in fragile families, that we're really making the most of that and not making mistakes. So, understanding the populations with which we work, understanding the context those data are collected is just really, really essential. My next point is that we think a lot about the possible trade-offs between accuracy and transparency. So for the Fragile Families Challenge, at least the way we approached it, we were just trying to get the best predictions as possible. But our models, we have no idea what's in there. I mean, it's a mess, and we applied maybe 50 different learners, and it picked some algorithm, and I can't describe to you how we arrived at these predictions very well, but that's not always going to work. So for example, I presented an example where we're doing a pretrial risk assessment. That's a case where we think it's really important that our model is transparent. So we're planning to have a very parsimonious set of measures. And some of those measures might be complex. But they might pull across a wide range of raw measures to have an aggregate summary measure. But then we also want to make sure we're not using too complex of a modeling process at the same time so that it's really clear how everyone's risk score was arrived at. And my final point is also probably obvious, But that prediction is not causation. And we need to be really careful in that we're not reading too much into the data. And machine learning doesn't solve this problem. I think in some settings, there's some thinking that if you use machine learning, you can just pull so much more information out of the data that you can make causal inferences when you couldn't before. But we still have the problem of unmeasured confounders. But at the same time, MDRC is known for doing randomized controlled trials to evaluate programs to understand what works. And a big part of these analyses is doing subgroup analyses. And so we'll often pick subgroups based on characteristics of individuals that we think makes them at risk. And so what we're doing more and more, I think, at MDRC is using predictive analytics to actually estimate that risk and pull together multiple risk factors and then use that for subgroup analyses. And in this case, we can make causal claims about what works for whom. And that's it. If you have questions, please feel free to email me. You can check out our MDRC's website. We have a lot of research briefs, 2 or 3 page papers that talk about how we approach predictive analytics. And you can also follow us on Twitter.
So, thank you, Kristin. Our next speakers are Erik Wang and Soichiro Yamauchi, who are both Ph.D. students in the politics department at Princeton. Although they are maybe 100 yards from us, they might, I don't know if they have heard about this study before. The challenge happened, and then they heard Ian present about the challenge in the quantitative social science seminar that we jointly co-organized between sociology and politics. And they also participated in the challenge in one of their classes. So the political methodology 4 is a very informative title, which is actually a course in causal inference and Bayesian machine learning. And so they will now present their approach with a third collaborator, Stanescu, who is not able to.
Flip this one. We're going to check the mic.
Can you hear?
Yep.
Okay. Okay, hi everyone. Thank you all for coming. Today, Soichiro Yamauchi and I are happy to present to you predicting material hardship using machine learning. And as Matt just introduced us, we are both from, actually all 3 of us, including Diana Stanescu, who's not here, are from the politics department.
In this fractal farming challenge, we basically deal with the 2 major challenges. One is the huge amount of missingness in the data set, but also the second challenge we addressed was how to deal with the high-dimensional nature of the data set. So we see that these 2 problems are in tensions because we want to impute the missing data, but it's really hard to impute when there are many variables. Then some of the variables not informative, but also we don't want to lose by selecting too much variables. To address these challenges, we came up with a very simple but very effective procedures that consist of 3 stages, which we're going to describe in detail in the later slides, but we're going to describe the processes in very brief. So in the first stage, we use the pre-processing, which is essentially the splitting the variables. That is the imputation stage that comes at the second. The point is that we want to minimize the number of variables to make the imputation effective, but at the same time, we want to keep the variables that are potentially predictive. So at this stage, we use lasso to purely screen the variables. And then at the second stage, we do imputations, which is kind of different approach from the previous speaker. And we did imputations for the covariates, but also we did for the outcome as well. Here we did the imputation for covariates and outcomes separately. And then at the final stage, as many of the participants did, we built a prediction model using lasso.
Yeah, so we choose Lasso for both data pre-processing and final prediction. And Lasso is known to handle high-dimensional data very well. It also helps avoid overfitting to the training data via penalization. And it differs from ridge regression because even though ridge also penalizes, lasso, the advantage of lasso is that it actually trims data by zeroing out certain variables. And this feature is very, this advantage is very important for us in the data pre-processing stage, because we want to first arrive at a much smaller selected group of variables, and then we do multiple imputation for that selected group before final prediction. And to arrive at this smaller group of variables in the first place, we need a method that can actually zero out other variables, and that's why lasso is used here. And also, as we all know, lasso also allows interpretable model selection.
Now we're gonna explain our procedure in detail. So here, the table is showing how the pre-processing stage works. So the first row 0 is the original data set. So it's basically, as we know, has like 2,000, more than 2,000, 12,000 variables in the data set. At the first stage, we remove the variable that has more than 60% of missing values. The idea was that if we have so many missingness in that particular variable, it's really hard to impute in the first place. So that's why we removed, and then we have 4,000 variable now. And at the second stage, we remove the variables, even though it doesn't have much missingness, but it has smaller variances. Then we remove those variables. And then we did the lasso to select the variables to go to the imputation stage. So that the idea we took it was that instead of naively fitting lasso for the values, but for that unit that doesn't have any NAs, we did a simple mean imputation before the lasso stage, so that we can exploit all the units to select the variables. And then we fit the lasso for each outcome, and then select the variable, take the union of all the variables that are selected. And then we go to the imputation stage to actually replace the mean imputation to the more high quality imputed values.
So after we arrive at this smaller group of variables, and we basically match them to the original data, so that the mean imputation, so that the missingness come back, right? Because we replace the mean imputed value with the original values, having a lot of missing, and then we do Amelia. We do multiple imputation via Amelia. In this table, and this is how we deal with the covariates. And we also did multiple imputation using Amelia, similar method for outcomes. And the reason why we do that is that we believe that there, at the individual level, there should be some correlation across these outcome variables, and we want, and I think information from such correlation structure should help prediction. And this table basically shows the number of NA observations across all 6 outcomes in the original data and also after imputation. And we see that after imputation, there are 655 observations missing, and this number is constant throughout all 6 outcomes because these are basically the individuals that have everything missing for these 6 outcomes. So these covariates, just to clarify, these covariates and outcomes are imputed separately, so that contamination is avoided.
Yeah, so these are a quick graph that's showing how imputation works. Only for the outcomes, it's really impossible to show the imputation result for the covariates because there are so many variables. So first of all, it's really hard to check whether imputation worked or not because we don't know the value a priori. But here, our validations or sort of like checking is that imputation didn't do much crazy stuff. So the gray bar is, so if you look at the bottom, the gray bars are the distribution of the original outcomes, and then blue bars are the ones after imputation. And you can see that the distribution is is relatively the same. So that's how we interpreted that the imputation work is fine. Yeah.
And basically, we implement lasso with our package GLMNet, and then the tuning parameter is selected by five-fold cross-validation. And this table basically just reports the number. So by the way, this is basically after imputation, and then we run lasso again. And this time we run lasso is for final prediction. And this table basically shows, reports the number of covariates selected in our final prediction model for each outcome. And we can see that there are 72 variables selected for material hardship.
So with those very simple procedure, you might wonder how it actually works. And then this is the sort of our result compared to the original dataset. Here we don't report the outcome, the result for the held out dataset. We just check in with respect to the training data. But you can see that, for example, material hardship, like we did pretty well in the sense that we didn't overfit that much, but the predicted distribution is very close to the training dataset, which means that we can kind of capture the functions that map the covariates into the outcome. Although we miss quite substantively in the GPA, for example, we predicted that most of the GPA in the middle, but actually it more split out. So that harmed the final results. Yeah, that's our basic results.
Yeah, so here we just we want to show some of the important variables in our final prediction model for material hardship. And here we are basically getting into some interpretation stuff. And I think we agree with the previous presenter that prediction is really different from causal inference. So we want to be very explicit about the limited nature of the interpretability of these results, right? So so the variable with the highest standardized coefficient magnitude in the model is not reported here because that variable is not really substantively intuitive. It's basically whether the child's teaching language in the child's school is an Asian language or not. And this variable basically it has a so the variable in the original data has a lot of missing and very few ones. So we suspect that the reason why this variable enters our final prediction model is that the variation is just driven by the imputed variable. It's basically the imputed variable that drives the variation. But these 5 variables are the variables that have coefficient magnitude size that are ranked the 2nd to 6th, right? So these are the second largest, third largest in terms of coefficient magnitude size onto 6th largest. So we have a lot of variables, but we just for time and space reason, we're just gonna report some like these 5 here. So we see that these 5 variables are actually pretty substantively meaningful, and then there's one common pattern across these 5 variables is that they all come from the mother side, and is substantively intuitive because these variables basically capture the financial hardship facing the mother, and which we believe is like substantively associated with the child's material hardship, and the fact that these top variables, right, from 2nd to 6th, all come from the mother side might be some suggestive evidence. Again, suggestive only because these are just like things in the prediction model. But we interpret it as suggestive sort of a larger pattern of single motherhood in America. In the sense that even though these families are all fragile families, they are fragile families in a particular way, in a way that the children usually live with mother much more often than the father, right? Therefore, information from the father side is going to be very, very noisy and tends to drop out of our model across stages. And Soichiro going to explain that in a little more detail in this slide.
So the figure on the right kind of confirm or kind of like confirm that intuition that the mother variable, the hardship of the mother predicts well for the well-being of the kids. So the two most left bars in the figure on the right shows the proportion of the variable in the original data set that relates to father or relates to the mother. So you can see that in the original data set that these two group of variables are represented equally, which I guess is supposed to be for the studies. But as you can see, as we proceed the variable selection stage, you can see that the mother-related variable dominates the father-related variables. So you can see that, for example, after we screen the variable and impute the variable, the mother-related variable is twice as much as father-related variable in the data set. And the two most left bars shows our results for the material hardship. So you can see that the mother-related variable strictly more represented in the final model that's selected by Lasso.
Mm-hmm. Yeah, so this final table just reports our actual results in terms of mean square error. So for material hardship, we did very well. So for the leaderboard, we have a MSE of 0.024, and then this MSE decreases in the holdout data, which because as we know, the leaderboard has some intentionally randomness in order to penalize overfitting, and I think our method, the fact that our method performs well in leaderboard, but also a lot more, even a lot better in the holdout than the leaderboard, suggests that our method works very well in what it's supposed to, which is to penalize overfitting. Yeah. Thank you very much.
Thank you very much.
Now it's my great pleasure to introduce Abdullah Almaatouq. He is a Ph.D. student at MIT in computational sciences and engineering. He also works in the human dynamics group at the MIT Media Lab. Several of the collaborators on this project are here, and also Abdullah first heard about the challenge at one of the Getting Started workshops. So we did a Getting Started workshop at the Summer Institute in Computational Social Science. Abdullah was there, he got excited about it, went back to MIT, assembled an amazing team, and they produced this wonderful contribution. So welcome Abdullah, and welcome to Abdullah's collaborators.
Thank you very much. Actually, we had to change the presentation during lunch for two reasons. The first, actually, what we thought is interesting before coming to the workshop was very different from what we think is interesting now. And basically, by having a conversation with such wider audience, we found that organizers, people, data providers, funders, other participants or researchers who worked on the data set had different interests. And it will be very boring to dive and really cater for only one type of audience among the interdisciplinary and the interests that exist here, and forget about the others. So what we decided to do is to talk more abstractly and really hit many of the points that we went through, and then give more time for the panel to take any direction that people find interesting. For the second reason is actually from a technical perspective, it's kind of a curse for going last, because many of the other participants faced very similar challenges, and many of their solutions were very similar to the solutions that we ended up using. So we are not too special from a technical perspective, actually. So I'm going to skip some of those details about it. So as Matt mentioned, I was a participant in the Summer Institute. We learned about the data. I found it really exciting. I kind of participated in other predictive challenges in the past, in Kaggle and things like that. And for some reason, they weren't as exciting. And that was a bit hard, actually, to figure out, because these other challenges would make you rich. And the fragile families will bring me back to Princeton, which I really like, by the way. So I went back to MIT. I sent an email. I knew what would motivate other people to join me. We are excited about the policy and scientific goals of the project. Everyone wants to help disadvantaged children in the US. I'll just let them know about the existence of this challenge, and hopefully I'll be able to assemble a team. In small print, everyone as well, we are graduate students, so we were interested in the promise of being able to publish something afterward. So we actually created an interdisciplinary team at MIT standard. So you'll notice that interdisciplinary actually coming from different departments, but these are the departments we have at MIT. So we have people coming from computer science background, computational and applied math, people from the new institute in IDSS, nuclear engineers, and mechanical engineers being interested in the project. And many of the team members as well come from very different places from around the world. So the first thing that happened after we noted our interest was, what should we call the team, or what's in common among all of us? And something that we discovered is that we all slept in the Pentland Hotel. And actually, this is a name that we give to a couch that Sandy Pentland, my advisor, bought that turns into a bed. And he has it in the lab for for students to actually spend overnights in the lab. He does not expect them to go back home. So we created the Pentlandians ensemble. We are all affiliated with Sandy, and started working on the project the same way that we work on hackathons and data fests, and when you have very short period of time to work on a project. Because as well, something to note is that I sent them the email almost on the 15th of July, and the deadline was on the 1st of August. So we really had a very short period of time. People had other interests as well in terms of their research advisors twisting their arms to make some progress on their own research. So we really wanted to do it the same way that we do it in hackathons. Really get your sleeping bag, sit together, work on nothing, concentrate on this project and see what you can do. And in order to be able to do that, we can actually use some of the principles from software engineering, right? Because we need to be modular. We don't have people, it's the summertime, so people wake up and sleep at different times. They actually travel, go back and forth, and it's very hard to actually conduct these, to work really in a more sequential way. So what we decided is, let's actually parallelize this. And actually, we can as well let's try to reduce redundancies, so things that will be repeated. Let's actually try to make sure that we think well about them and do them really early on. And then let's harness the wisdom of the crowd, or at least let's have people work independently. Some people say that MIT students in general, they are not very social and they would prefer to work independently. But let's work independently. Let's hope that different people, by maintaining that independence, we actually will, idiosyncratic errors will cancel out. So if someone will somehow overfit, someone else will underfit, and hopefully that will average out. So we really did that. So each individual, we prepared the data, and I'll go a little bit in details of what that means. That's kind of the reducing redundancy. Then we talked as a team of each individual, what do you want as an input, output, really? It's like modular black boxes that will feed into each other. And then people will work on it independently. They'll use different feature selections. They'll use different models. They'll reason about why they are making their decisions by themselves, and really trying not to maintain that independence, at least for a certain period of time. And then they can share their final predictions with me, where I have to do my own magic for creating that ensemble, which is this function in Python that would take everyone's prediction, create some sort of an ensemble, and then submit it to the leaderboard. And that's how I take more credit than others in the team. So something that we really were worried about to begin with is this leaderboard. I didn't hear many people talk about it, but it's really just, we believe that just looking at the leaderboard makes your performance worse. It's if you can be blind to it, resist the temptations, because really the data set is not too large. And one of the main concerns for machine learning, we are not used to this type of data sets, as Honor has mentioned. We like tall matrices. All of these fat matrices have all sorts of issues numerically and all type of problems that we don't like to look at. And one of the main problems is this curse of dimensionality. Just because we have high dimensional data, we can, and the leaderboard is really small in terms of observations, that we would fit, we were concerned that we would overfit the leaderboard. So we really had a lot of rules of how to avoid that temptation and really focus on the cross-validation and be extremely careful for overfitting when you are constructing your models. So the data preparation includes things for everyday cleaning stuff. So we have the missing data. We did similar things as other people did. One of the problems was this treating data differently based on whether it's continuous or categorical. So we search the text, the structure of the question, and try to infer the type of answer to that question in order to be treated differently. As well, missing data. We believe that missing data, as many have already mentioned, have some information in them. So we did not want to just throw them away or even impute them, but actually add indicators. If someone refuses to answer, is very different from if it's missing because of a skip or some other type of missingness. And we did not really, we actually tried Emilia for some time, and people know that it has some computational issues. So we really had this cluster on Amazon Web Service that would run it in parallel and finish. But then we decided not to really go that route, just because the assumption of this multiple imputation that missingness is at random does not really hold. And once you actually add these indicators, you end up with very few missing values that might not be worth it in the continuous ones in particular. So we do believe that social science can compete. And that's why we actually wanted to integrate substantive knowledge of social science and many, many years of research that was conducted on this study into our models. It was hard for us to actually reason about this, given the background of many of us and the type of research that we do. So we did the second best thing that we can do, which is creating this web crawler that goes to the website that has the list of all of the publications that are published using the Fragile Families dataset, download all of the papers, look at the text, index it, search for every paper that used one of the 6 outcomes as its outcome variable, as its dependent variable, and then let's try to see what was the R square, how much did it actually add according to the social science theory, and then rank them based on that and try to reconstruct them. It was a lot of fun, except that it was really hard to reconstruct them. Everything worked except that. Because many of the papers that we encountered actually, I was telling Matt yesterday, is not the type of papers that we are used to, because it even misses, when they have a regression, the functional form. So once you go to look for the independent variables that they constructed, which is some sort of transformation of the existing raw data, looking at things whether both parents have the same level of education. So it's not just like differences in level of education and things like that. They don't provide things like the name of that variable, and there are 12,000 variables in the data that it's very hard to find which one it is. And we ended up only being able to reconstruct 10 of those variables, although we ended up with a much larger list that we wished to include. Then high dimensionality, so we really need to be aggressive in feature selection, as many have said, and we were trying to really try different methods and be really conservative in terms of when we do the feature selection. Then the individual magic that I told you about, each individual took this data that is now prepared. They did further feature selection based on why they think, for any reason they had to think that this is a good approach to do feature selection. They created a model, they made predictions, and then they sent it. We centralized them, aggregated them, and submitted. So by submitting, we actually tried different ways of aggregation. Something like the simple average of everyone, or estimating the weight. So it's some linear combination of the predictions of others and keeping it simple using just something like a linear regression to estimate those coefficients. And then we did more complicated stuff that I'm not going to talk about. And they didn't work well as well. So, so the outcome of that approach actually did surprisingly well. We were able to come first in 3 out of the 6 outcomes. And the MIT News wrote about us, which is really cool. So I'll go about some insights from those results. Retrospectively, after the challenge has finished, we can go back and actually check other models that we decided not to submit. How would they have done on? How would they do on the different aspects? And really look if there are. Try to debug our approach in some way. And unfortunately, I think we were cursed by looking at the leaderboard. There is something that I did not mention about the rules that we established as a team in order to allow your model to enter the ensemble that we created, which is you have to at least try hard enough to be among the top 15 in the leaderboard. So if you actually submit something that is not necessarily in the top 15, then you know what, we'll just skip your model. And I think that actually gave an incentive for many people while trying to avoid overfitting to the leaderboard to actually to fit to the leaderboard. And this is something that is evident that if we look at the best model that we had in terms of cross-validation or on the leaderboard or on the or some of the models, how would they perform on the holdout data set, you will see that we made decisions that weren't necessarily, we made the choice of removing models or substituting models that they would have done better on the holdout data set. And the reason behind that was they did poorly on the leaderboard. So feature importance, because we can go back and look at the feature importance of the models that we have, we found out that what we learned is that what is important for the model is very different for what is important for people. So actually, by showing some of the top features that or variables that explains that were predictive in this exercise, we thought they make sense. If you look at more features, some of them wouldn't necessarily make sense very quickly, but we have Duncan here who would tell you that everything is obvious once you know the answer. So we were actually able, even when we had bug in our code, we were able to create all of these hypotheses and stories about what signal it might have been picked up, and we really create a narrative around it. But what we can do is actually help and hopefully use these feature importance to be suggestive for further investigation. Because if these, by understanding actually how these algorithms, because they are not straightforward linear algorithms as well, but by understanding how do they assign those weights, and which might is picking up some proxy for a signal in the data set, it might actually inform new social science theories, and it might actually provide directions for a more guided search in the space of possible hypotheses. One thing that we looked at is when, so we aggregated the importance of these features across times and people, respondents. And when was the most important features for our models were in wave 5, except for material hardship, it was at birth. And again, this we found this interesting, and at the beginning we were sad because we thought it's an anomaly and it's something that we will have to explain, but we are just reporting it. It's up to you to explain what actually it might mean. The other thing is the who, and you see that for all outcomes, the most important respondent for us was the mother. And we hope that these results will be helpful in really guiding the search for hypotheses, as we said. There are several of the challenges. They were already mentioned, like we like the tall matrices, not the fat ones, but this is actually realistic in computational social science. We'll be facing more data structures like that, and our methods should actually be for people who are trying to motivate this computational social science approach should be careful about and develop methodologies for it. The other thing, it was really hard to exploit the structure of the data because the data is really complex, it's really large, and there is a lot of hidden structure that people could exploit. So there is a need of a roadmap in order to be able to further improve the predictive power. So something like metadata is great. And finally, we were frustrated because according to the type of research that we do at the Human Dynamics Group, which is a lot of passive data collection and trying to measure how community and factors affect outcomes, we were frustrated that many of the data points, the columns or the features that we thought important were missing. And they were missing when we asked because of risk of re-identifiability. And I think really there is this trade-off that Matt talked about, and in the workshop there was a paper talking about it, which is how can we really think and reason about the trade-off for usefulness for the researchers, for the risk of re-identification, and how can we foster a conversation between researchers and data providers in order to be able to have some framework that allow to unlock the potential of such data set. So this is my time. Thank you very much, and please ask any questions in the panel.
Extra chairs for
Please.
all of the.
Clearly the large teams in the final.
I think good. Fantastic. So 3 really amazing presentations from a really wonderful group. And so let's have some questions.
Talking about with your team use basically an ensemble method of just the top model because they all have to be in the top 15 on the leaderboard. So actually my question is, did you all, in your community model, did you all use, is there a threshold of the performance on the leaderboard?
Yeah. So
Sorry.
yeah.
Or did you all use-
I'll talk about that in a second. Do you want to talk about how you did a little bit more about how you did the ensembling? Because that's something we struggled with.
So yeah, we tried to keep it simple. So at the beginning, we just, because each of the models actually for continuous or for the categorical variables, we predict probabilities. And then we just take the average of everyone's prediction. And they had to be in the top 15. And we weren't very actually strict about that rule as well. So there is a model that was ranked 17 that we still included it. And then to estimate these weights, actually we did, we based it on cross-validation, so average of many cross-validations on the training data set that we had. I don't know if this answers your question or if it's a little bit.
And then
So how did we do it? In our position as the challenge organizers, we were not as able to not accept people's contributions. So we really wanted to include as many possible models as we could. We did some deduplication because some people contributed exactly the same predictions, and that was not adding information. And then we dropped ones who were doing worse than the baseline. So they had the rule of being in the top 15 in leaderboard. Ours was the baseline. And so it's possible that we might have gotten better ensemble if we had had a higher threshold. We don't know. What will happen is that when we publish the paper with the big ensemble model, we'll release all the predictions. And so other people could try different ensembling strategies, and it's possible a more sophisticated one would work better. Also, David Liu is working on a different ensembling strategy that involves actually being able to run the code of each pieces. So our ensembling strategy was a sort of stacking-based approach, which is yours as well. And it may be that there are other ensembling strategies where if you can run the code, you could potentially do better. And so for everyone who has submitted to the special issue, your code is in the process of being reviewed and made runnable. And then we'll be able to try a variety of ensembling things with that code. So it's an open question.
Since you all got tops, I guess, scores or predictions, what is y'all's opinion on the fact that in general they are all pretty still bad? And do you think it's a matter of just getting, more magic, more brilliant people, or do you think it's maybe not possible to predict these things using machine learning at all? Given that maybe we're not measuring the right things, and maybe the right things aren't measurable, there's a lot of.
So I have a really good candidate of possibilities, but all of them actually were taken from a conversation I had with Matt. So, I'll probably Matt is going to talk about it as well at some point. So, so at least some of the ones that come on top of my mind is it this gap between year 9 and year 15? It might be it's relatively a big gap. Even weather forecasts and things like that, we do them. It depends on how far in the future are you trying to forecast, and maybe especially between 9 and 15, there are so many things that actually happen that can affect that the models are not looking at. Other possibilities is human behavior is inherently unpredictable. And this is we are reaching the limits. So this 0.2 R square or something that the models reached is what it is. Or it might be missing on some important features or variables that are not necessarily asked in the previous waves. And I believe that's one of the main points of the challenge is to really identify what Matt has been calling the what did you call it? The dark matter of really guiding the survey questions in order to find and search these things that can explain the variance. And I'm sure as well, Matt and others can elaborate on this.
I also have a technical answer to that. It's a guess that probably a lot of the outcome variables are concentrated within a very fixed range. So with that evaluation metric of mean squared error, if you want to be a good model, you have to fit those ones that are in the middle of the concentration. So that's why you probably miss a lot of the data points that are in the sides of the distribution. That's why we had that plot that Matt showed. There was a lot of inaccuracy on the sides of the distribution.
I have a follow-up question for Kristin. So it seems like you've done a lot of other predictive modeling tasks somewhat similar to this in somewhat similar populations. And so I'm wondering, what are some characteristics of outcomes or data sets or combinations of outcomes and data sets that you see where prediction is highest and where prediction is lowest? So this is maybe another way of asking, like, is there some kind of fundamental limit, or sort of if you think of the space of all social prediction problems, what are the important dimensions there, and how does this particular challenge fit into that bigger space?
I think where we've had most success is in predicting things that are highly dependent, of course, on what we're collecting. So for example, high school graduation, it's very commonly predicted. And it's also largely a formula based on your course completion in some school districts, whether you're passing required exams, so on and so forth. Other things in K-12 education that are then harder to predict are things like attendance, because they are inherently, there's just a lot of randomness, whether a student is, has some sudden tragedy in the family or suddenly sick. So these things are something that we also try to predict, but are much harder. We are also, we predict a wide variety of outcomes, but we also predict them at different points in time. So for example, we're currently working on a job training program for ex-offenders and people just coming out of prison. And our first time in which we're trying to predict whether they're going to complete an important job milestone in terms of being placed in a job is when they first come in the door. And so at this point, we just know background information on them in terms of their education level, in terms of how long they were in jail, in terms of how they arrived at the front door of this program. we're doing okay. We're doing better than a random guess. But as time goes on, we're bringing in more and more information. So we might look 1 month down the road, and now we have information on whether they are showing up for their activities. We have case notes that we can text mine. We're not doing this at the time, but this is something we plan to do eventually. And so as we pull in more and more information, it's also closer and closer in time. Our predictions are, of course, improving.
That's actually another question. You said MDRC?
Mm-hmm.
MDRC, you are doing pre-trial risk assessments. And I'm sure, I guess you've heard about the ProPublica and the bias that they saw there were the criminality risks.
Yes.
So what measures are you all taking to mitigate bias? I guess one of them is transparency, first of all, using interpretive model. What else are you using to mitigate bias?
Yeah, this project is just kicking off, and it is a new area for me. And I think a lot of the debates around the ProPublica article and the debate that followed it is that there are so many different ways to define bias. And so we're going to be working closely with the funder and looking at a variety of ways to define bias. Another important thing that we're not able to measure is how does the bias of this tool compare to the bias of judges had they not had this information available to them. So that's an important, I think, argument to consider. There's just only so much information that an individual can hold in their head. And so the measures that we're going to be combining into a risk score through predictive analytics are the measures that these judges already have available to them. But it may be like 20 different things, and how do they know how to prioritize and weight those different things? So we're just trying to add an extra piece of information that helps them pull all of that together.
I have a question for the audience. I'm wondering if you guys went into the challenge knowing that you would use lasso. I find it really interesting that something that it's not too complicated to understand, doesn't require a lot of computation power, can still do really well. If you guys had tried more heavy machinery and it didn't produce as good results, and then you went back to lasso, or if you just knew that you would use lasso from the start.
So our approach was trying to be very simple, because we know that the data set is not that huge in terms of observations. So for example, if you do convolutional network, it's not going to work. And so and also our time was so limited. So we wanted to try to very simple at the same time, so very works better. But we also tried the variable screen technique. So we did the lasso twice, but we also tried some other variable screen technique, but it didn't work that much, and it ended up the lasso works the best. Yeah. Do you have anything?
So I also have a question for your team. So I thought the idea of imputing the outcomes is interesting. It's something I experimented with too. And it's kind of a strange task because it's really what we're doing with the predictions as well. So I'm wondering how you thought about this and made the decision whether to have a kind of preliminary model to compute the outcomes and then another model, or using a kind of multiple imputation technique to do that. And I'm wondering if anyone kind of in the room just used multiple imputation to impute the challenge outcomes and saw how well that would do in the challenge. It would be interesting to see how that compares to these machine learning approaches.
Right, so so we imputed the outcomes before making prediction just because we had the vague idea that perhaps just taking advantage of, because if you don't impute, you end up with just a lot more missing them than currently, right? So you're just losing the information, and we kind of want to just add some information. And the idea is that at the individual level, these outcomes can be correlated. But actually, when we actually check the data, they are we seem to overrate the amount of correlation across these outcomes. So that might be a step that was not necessarily necessary. We just did it because we had this vague idea. Yeah. But do you want to say?
Yeah, so there are methods that can actually predict multiple outcomes. that are designed for this, that you don't actually have to impute. You can define a model, build a model that makes a prediction for 6 outcome variables. So our group actually did try that, and we actually ended up using the single outcome prediction because it didn't do as well.
Since the winners are more like using the ensemble learning nonlinear models, as we discussed before, that there's a trade-off between transparency and performance. And it's more like we won't emphasize performance, then more black box algorithms and machine learning models are involved. So what would be the future, like how to control this trade-off? It seems like it will be pushing to the black box size and then become less transparency. Is any
I think
thoughts?
they could. You all have thoughts on this, I'm sure. Yeah?
Yeah, so what I thought so like one of the rationale that using the simple lasso was that after we get the result, it's really easy to interpret the result because you have the variable that are selected, so you can basically look at the code book and then see what's in the model, right? But whereas like if you want to do, for example, causal inference, you don't necessarily care about what's in the controls, right? In that case, like for example, I'll rather do like splines for those variables and then make more and more flexible, and then control for it. And then what we care about is a treatment effect, for example. Like that's the tension what I kind of thought about in this exercise. Yeah.
Actually, as well as a response, I want to use an example I heard from Sandhel Molinathan, who works on machine learning for policy, where he said it depends, this question or this trade-off depends on the type of decision that you are trying to make. If the decision is whether to take an umbrella or not, you just need to be able to accurately predict the weather. But it's very different understanding of the system that you need if you want to do the rain dance to make it rain because it's been a drought. And it depends on what type of decision do you want to make. The importance of being able to interpret or predict is different. And I mean, Matt and the organizers of, for us, kind of when we usually participate in some of the computational social science kind of conferences or venues, there is always this discussion. Is that what you're showing us? Are you trying to interpret it causally or not? And that's why we usually try to avoid that discussion. But the organizers and Matt had the consequences of the challenge, something like good predictions would actually help with. For example, we are not trying to predict eviction in order to be able to design an intervention to get people not evicted, but maybe, or for someone who is not doing as well in their school, we are not trying to design particularly a change in their environment to make them do better, but maybe we can predict people who are potential targets for these programs and then go and do further interviews. So you can use these predictive models as a way to target participants, to investigate further, to actually run RCTs that are hard usually to do, and in these cases they are probably sensitive in a more educated way of what type of outcomes do you expect, and not necessarily, and for those things, as well as Matt said, you can use these predictions as propensities, and people who do causal inference, it's a statistical method that's filled with assumptions that not necessarily hold about the covariates and observables and things like that. But again, it uses some simple method to get the propensity, which are two observations have the same propensity of getting some treatment, and one did and the other didn't. And basically, if you can increase the predictive power to use them as propensities, then you are, again, you want to maximize prediction, and interpretability doesn't have to come from the same model, but actually it can come from follow-up studies that will identify those observations that are worth investigating further. So really reducing the space of potential interventions and a targets to the intervention.
I have a comment there and then maybe a follow-up question of everyone else here. One thing that perplexes me and that I've been trying to think about with respect to variable importance is that it feels like when we're doing machine learning, we're recognizing the fact that just on average indicators are not enough. We're interested in interactions, for example. But when you go back to looking at the key features, we're just back to talking about averages. And what we really care about is, why is this person at risk, or why does this person have this predicted probability? And I know I've been reading a little bit about some methods that have been trying to get at this tension, and I'm curious if any of you have tried them or have thoughts on that.
Tom, I think I'm going to highlight your paper for a second. So the question of interpretability, I think one of the things that I noticed from looking at all the papers and talking to the participants is the amount of time that went into model building and data cleaning was often really big, and then the amount of time that went into model interpretation was almost zero. It was like an afterthought. Except Tom's paper, I think, was different in that he spent a sizable amount of the paper on trying to interpret the complex model. So I think if we treated model interpretation as an important part of the research process, then I think we could potentially learn something from these models. And I think, Tom, do you want to talk about what you did?
To get to your question again, one of the problems here is I applied an algorithm that can help to explain what's going on inside a neural network, which is a much more complex type of model. But the problem is the algorithm is recovering important variables, and it has some linear explanation for that variable. And in fact, what's going on in the model is a lot of complex interactions and non-linear functions of variables. So although we can recover some information from black box models, it's very hard to know what's actually truly going on inside the model in terms of these non-linearities.
Can I say one more thing about this question too? So we've thought about this trade-off a lot, and we think one of the great things about this trade-off between interpretability and performance is usually asserted, and it's actually an empirical question. And here we have many, many models using a variety of techniques. We have a clear measure of their performance in this setting, and we'd like to have some measure of their interpretability, and then we can make a scatter plot and see. But it turns out that quantifying the interpretability is very complex, is really hard to do. We hope that this is an example of one of the kinds of things that can be done after the challenge. So after the challenge, all of the code from the models will be released. All of the predictions will be released. People can try to identify this trade-off empirically in this setting and see how severe it is. And my intuition is that it's not as severe. It's true that many of these models did use harder to interpret results, but my guess might be that the performance penalty is actually pretty small to get an interpretable model, but I don't know, and we would have to see. Duncan?
So it seems like there's at least three things going on here, right? So you have predictive performance, you have interpretability, and you have causality, right? And I think that if you just look at the trade-off between performance and interpretability, in practice it may not be so bad. That, like, very often you can find a relatively simple model that does about as well as the most complex model. But it doesn't mean that it's doing the same thing as the more complex model, so you still don't really know what's happening. And then you also don't really know whether the simple model is doing any better at identifying causality. So, this is not my area, but does anyone, there's like some kind of, manifold in this three-dimensional space of, like, the frontier of what you can do, and I don't have any idea what that looks like.
Do you all want to comment on that? You want to? No. So I think for the causal inference question, a big issue is really the unobserved things and the things that are not in the data, and whether selection on observables is an appropriate assumption or not. And so then we need to know, what are these unobserved things? What is the vast white space that we saw in the morning? And one of the things that Sarah and I will talk about in the last panel is how we're going to try to figure that out. And I think that will have implications for causal inference. So I think that
these predictive models may not directly lead to causal inference, but they can help target future data collection, which can then be informative about whether causal inference would be appropriate for which outcomes.
So selection on observables here with the assumption that the treatment is like as if randomly assigned conditional on the covariates, put simply. So something that we would like to say about the community model, which I can say from having looked at it like heavily weights all of your submissions. We would like to say that that accounts for all of those 12,000 variables that we measured from birth to age 9. But obviously it can't because there's a large P problem and because machine learning methods use some sort of regularization that often like throws things out. So one question I've wondered in thinking about interpreting what we've got here from the community model is sort of which of those variables have we sort of included and which have people not included. So for instance, Erik, Soichiro, and Diana, I think you threw out any variable that had more than 60% missing. And I've heard other people say that through the day. So thinking about like on our end, what can we think went into these models? I wondered if the other groups could say, did you throw out variables that had more than a certain proportion missing?
So yeah, for us, we threw out any variable that had over 80% missing, I guess. So we set a slightly higher threshold, and that's partially because we imputed using the mean as opposed to multiple imputation, which relies on more observations for any given variable. We also removed features that had very low variance. I'm not sure if other people were doing that as well, but of course, like if you're running a model, you want variation in your X to actually be able to predict anything.
We took a similar approach. We eliminated variables that did not have a particular meet a particular variation threshold. I can't remember exactly what it was. And in our submission, we only used the survey information from the mother, father, and primary caregivers.
This is a question to all of you. And kind of following Matt's point, when we think about the kind of variables you guys had to use, which is there's answers to survey questions, and the fact that you didn't have a lot of identifying variables, so geographic data, medical data, I don't know if you could use that, but are there other layers of information that would have been interesting, like, or do you use that commonly? I'm thinking like social networks, or as Abdullah and I talked about, phone movements. Like, are there things that you're more used to working with than what we have, or advances that have been made in terms of survey questions as well?
I just have one quick response to that, something we didn't do but a colleague suggested, and that I don't have experience with personally, but is to do a sentiment analysis. The idea being that some people may respond to research questions in a more optimistic way, or other themes along those lines that you might be able to pick up and use as features in your modeling.
I'm not sure that this could answer your question, but one thing I really wanted to do, but we didn't have the computation power to do, is to investigate interaction between different variables, because I think that would be also very important. But we didn't include any interaction in our models.
I think we can't forget that. And Steve, you got like really good accuracy with using only 4 feature variables. So how does that change the way you view your own approach, and how do you think that will inform your approach when you tackle similar problems?
I think that speaks to domain knowledge, and it shows how important that is. So I would say our team was mainly composed of data scientists. So if you had some person with some domain knowledge, maybe we could have done a lot better.
And actually, we really, because of the nature of the data, again, because we have many more features than observations, we weren't confident to begin with that actually machine learning methods will do well. We wanted to participate in the challenge anyway and try our best because we thought it's cool, but we really didn't expect it to do well in just because of the nature of the data set. If it was a tall matrix, I would be more confident that actually we would do really, really well in comparison to people who pick very few variables and try to use domain knowledge. But in that particular case, we weren't confident. And we tried to get more social scientists in the team, especially like sociologists, and they didn't end up working with us, and that's why we created, because we believe in that, we created our web crawler, which is okay. If we can't have the real one, let's have an automated one that it's not as good, but maybe we'll extract some of this knowledge. And I think, or I believe at this point, that if we had Steve with us on the team, we would make even the variables that he ended up constructing even more predictive by using cross-validation and a little bit more parametric methods. So I really think the combination would actually reduce that white space in some of the outcomes.
So I have a quick comment on that. Go ahead. Yeah. So I have a quick comment on that because I think oftentimes our substantive knowledge is like heavily tilted towards causal inference. So for example, some people in our department might just write an entire dissertation on just the causal effect of one variable. So it's important, right? Because we know the effect of a cause, and then you can also have more qualitative understanding of the causal mechanism, which is the cause of the effect. But in terms of prediction, right, you actually need knowledge that explains the whole, that explains the whole thing. It's not a knowledge about how a particular variable matters. It's rather a knowledge about what the entirety of the variation in the outcome. And I think there is so it is this sort of gap that can make using substantive knowledge in prediction a little more challenging than we think.
As I pass it to Yoshi, let me just make a small comment, follow-up. But as well, I think the main, the importance of the social science challenge is the variable transformations, because as you saw in Steve's, for example, case, he did not pick up any 4 columns, but he actually constructed some non-linear, very interesting interaction between these variables to construct his variables, which are missing from our data set, for example, and then our algorithm will not be able to pick up those variations, at least not necessarily as easily as if it was provided.
Finally get a mic, and already Abdullah and Erik explained what I wanted to say. But yes, I feel like the starting point of this challenge is that we somehow assume that all the 12,000 features are independent, which is totally not true. So some features should have more aggregated information. And he was really good at finding the 4 features to make it right. And so I remember I talked with Matt about this idea, is that it would be interesting idea if we have a restriction for participant to only use, let's say, 10 features, up to 10 features, to create a predictive model in order to make a better interpretation with a limited amount of features.
Yeah, I have a quick question to ask you. So I thought the multiple imputation is going to work. But my simple question is that when you take into account the missingness pattern and you create the dummies, right, is that actually ended up at the final stage? Are those variables really predicted? That's simple curiosity. But
I don't remember. So we actually did, and what was really interesting is that sometimes we had a couple different answers that showed up as significant. So for example, one of the questions that predicted eviction very well was, has the telephone service been disconnected in the past 12 months? And that showed up twice, and I think, I'm not completely certain because we actually removed the answer from the paper for now. But we'll put it back in. But I think the answers were yes and actually refused to answer. So what was interesting is that not only the answer, but also the missing codes were indicative of an effect that we used to predict that. Does that answer your question?
complex models that maybe do a little bit better than the simple models. But it seems likely that lots of simple models will do similarly, right? Because you have a lot of these features and many of them are correlated. And so what do you do about interpretation when you have many models that have similar performance, but they have different sets of independent variables? If you just had one of them, you'd be okay, right? You just tell a story about it, right? But now you have sort of 6 or 10 or 50 of them, and they all tell different stories. So what do you do with that?
I think it just highlights the limitations of making causal inferences.
I would focus on the gap between the feature importance of the models. So this is something feature work, our work, is that our work takes into account the multiple interactions, combinations of features, which couldn't be partially explained by the simple, like a linear model. So we might want to focus on the gap between the feature importance of our model and the simple linear model, so that what could be explained by our model, to find out.
Models, full of complex models, we don't know at this stage.
So this is something we were really worried about in terms of people potentially drawing the wrong lesson from the challenge by just focusing on the top performers. And so we have a couple ways we're trying to deal with that. One is we're going to release all of the code and all of the predictions for all of the submissions. And then the second is in the special issue, we had to, in the end, we finally found a journal that appreciated this exact concern, and we said that we don't want to only publish the highest scoring things, we want to publish anything that is scientifically appropriate. So we have tried to set up the challenge in such a way that we avoid this problem, and I think it's an open question, sort of how we characterize the full space of submissions, because we can, for the people who have taken the time to write up what they've done, we can read them, and even there it's kind of hard. And then we have many more submissions where we are trying to learn about them from the code and a very sparse narrative explanation. And so one of the things that's, I think, going to come next is what can we learn from all of that code? This is something Alex is going to work on. Do you want to explain a little bit about what you're going to try to do?
Heuristically on the answer to your question, and then I can say a little bit about the broader measurement strategy. So just from looking at very schematically looking at the code and its relationship to people's scores, there's the relationship is surprisingly weak. So there are lots of people who applied machine learning techniques very poorly. And lots of people who, the relationship isn't as strong as you might sort of expect. More generally, so one of the cool things about having this big sample of code is that that's a kind of data on the distribution of methodological practices that has never really existed before. There are, and the code kind of gives us a trace of that, right? So if you type regress into Stata, then we have a sort of idea about what kind of techniques you used. Or if you import the Amelia package, then we kind of have a sense that you might have done multiple imputation. So at scale, we can sort of map out what the different approaches people took were. And then since we have the scores of all those models, we can sort of relate those to performance. So we're going to try to sort of think about how to characterize and describe that. Yeah, one of the limitations is that not all of the code is sort of complete. So there's in addition to there being missing data problems in the challenge, I have a big missing data problem.
Yeah. So in this discussion, there's been sort of a question of how much are we reading too much into the winners? And like you all did a great job with your contribution, and you had the best score at the end as defined by the challenge. But I will say that in the process of building the community model, we re-estimated the scores with one respondent left out each time, and it's not the case that these teams always won. So occasionally there was a different team with a better score with just one holdout set changed. So really, like when Matt said in the beginning, there are these, like the top 10 performers should all be like seen as very worthy and contributing a lot. They all do often get substantial weight in the community model, and like, you know, these teams are great and we should celebrate their job, but also everyone else, you know, if you had a good model, you've contributed.
Can I add on to that one too? One of the cool things about having this like submission history for each of the users is that we've gotten to run now that the holdout set is open, we can compute like how they would have done if they had like stopped at a certain point. The rate at which people's scores, their final scores, are worse than like what their score might have been if they had sort of stopped is pretty surprising. So, you know, it could have been the case that if everybody had like perfect information about where to, you know, like what was going to perform well and where to stop, then the distribution of winners might have looked a little bit different.
So thank you all. This was a really wonderful discussion. Let's thank the speakers again. So we have now a half-an-hour break. This is a chance for us to continue these discussions more informally. And then we'll come back at 4:30 for the final talk about what comes next.